Okay, good morning. Thanks to some of you for braving the cold this morning. Just to orient us as usual, your undergrads assignment 3 is due tonight. Grads 5 and 6 is due tonight. Later this morning, I will post assignment 4 for the undergrads and 7 and 8 for the grad students. Any questions about any of the assignments? So far, so good? Okay. All right, back to lecture material. We are going to finish up this morning our discussion of the last 3 of the tools of the trade, physical simulation. We'll finish that up, and then we'll move on to the next module of the course, a very brief history of evolutionary robotics. The first evolutionary robotics experiment was conducted back in 1992, so it's a relatively new branch of robotics. So we'll spend 7, 8, 9, 4 lectures on the history of evolutionary robotics before moving on to locomotion and our particular brand of it. Okay, so back to lecture 6, physical simulation. We ended last time by talking about that part of physical simulation that is the most computationally inefficient. For every pair of objects that are in your scene, at every time step, the simulator has to compare every object to every other object, which results in about n to more or less n squared comparisons. We talked about how this is derived last time. So in the first assignments, you're going to be working with a very, very simple robot made of a few components. But as you start to create more complex physical simulations with more and more objects in it, the fan on your laptop will start up and things will become computationally expensive very quickly. That's part of the reason why we're spending so much time talking about collision detection, determining whether or not there's a collision, and then collision resolution. What does the physical simulation do once it detects a collision between a pair of objects? We finished last time by talking about collision detection. Let's move on to collision resolution. Again, the code snippets here are from a different physics engine and a different language, Open Dynamics engine and C, respectively. I don't expect you to be able to read this code. I just wanted to point out a few things about at least how ODE handles collision resolution. It's a little bit different in PyBullet. In Open Dynamics engine, there is a callback function. So this is something that some of you may not have seen before, especially if you're not a computer science major. There is a form of programming called event-driven programming, which is your computer is detecting behind the scenes whether or not certain events happen. And then when an event occurs, your computer jumps to that point in the code, that callback function. Most of you are used to coding by writing your code, and you know that your computer starts at line 1 of your code, then goes to line 2 of your code, and so on. And your computer pays attention to one line after another in the code that you write. Event-based programming is a little bit different. The attention, where your computer is attending to, can jump around from different parts of your code if events happen elsewhere. So this is one of those situations. So this particular piece of code sitting inside the ODE physics engine would be called when one of these comparisons says this object, object 1 and object 2, are very, very, very close to one another. It looks like they're colliding. I'm pretty sure there's a collision detection event there. So at the moment we have O1 and O2, 2 objects which have triggered the call of this function. So the computer now starts executing the lines inside this callback function. It starts by using the geoms. You remember last time we separated the description of every individual object into a body and a geom. The body describes the mass properties of the object, and the geom is like a skim that describes the geometric properties of the surface. As you can imagine, if 2 objects are approaching one another, the physics engine uses the geoms, the geometrical description of the objects, to determine whether or not 2 objects are in contact with one another. Even this event, we're kind of skating over a lot of the details. The simplest case for collision detection is spheres. Imagine O1 and O2 are two spheres. How does the physics engine determine whether or not these two objects are in collision with one another or not?
If their distance between the two centers are the same as the radius?
The radius of, so you mentioned the centers of the two objects.
The sum of the two radii?
The sum of the two radii, right? The radius of object 1 and the radius of a sphere 2. And obviously, if the sum of these is if the distance between their centers is less than the sum, they're in collision with one another, right? Trivial. Imagine sphere and cube. It's a little too early in the morning, right? It gets trickier quickly. So even doing all of these computations, some of them are cheaper than others. If all you have in your simulation are spheres, this is a little easier. If you've got a collection of spheres and rectangular solids, it gets more complicated. Okay, so for our purposes, we're assuming that the physics engine is using the geom, the skin around the objects, to determine whether they're in collision with one another. First thing the callback does is for each of the two skins, O1 and O2, get back the bodies associated with those skins, the things that are inside, B1 and B2. And again, if you can't read C, that's okay. What it's doing here is asking if these two bodies exist, B1 and B2, we'll ignore that for a moment. And if they are connected, we're going to ignore the collision. We're going to return out of this callback function. This callback function gets called when the physics engine thinks O1 and O2 may be in collision with one another. If those two objects happen to be my lower arm and my upper arm, and the physics engine determines that those two objects are connected, it should ignore that collision. Why?
You don't want your arm to repel itself apart?
Absolutely, because if the collision is resolved, meaning the physics engine is going to say, yes, there's a collision, and I'm going to start trying to literally push these objects apart, that's probably not what you want if you've connected them together with hinge joints. Yeah. Okay. It gets a little more complicated because it's asking, are these two bodies connected, excluding a particular type of joint, which is a contact joint, which we haven't talked about yet. It gets confusing. We'll come back to that in a moment. So there's a whole bunch of situations that it's trying to determine, and if all of these situations are true, then you don't need to resolve this collision. There's a collision occurring, a collision detection event has occurred, but you don't need to resolve it. You don't need to do anything about it. If the computer does not return at this point and continues further into this callback function, indicated by the dots here, what the physics engine does is to spray a number of contact points in the three-dimensional region where it thinks those two objects are in collision with one another. So if we go back to our two spheres that are colliding, the physics engine is pretty sure that this is where the collision event is occurring, and it will drop a bunch of contact points into this space. It's going to use these contact points to simulate the collision between these two objects. Intuitively, the more points that it drops into this region, the more accurately the physics engine is going to be able to simulate that collision. In the case of, for example, two steel ball bearings coming into contact with one another, it's a simple collision. They should just repel in the opposite direction. I want you now to imagine that you and your friend have Nerf guns and you shoot two Nerf balls at one another. These foam balls approach one another. They hit. They start to deform. It's much more complicated how they should be pushed apart. And so the physics engine is going to use more points to simulate a collision between more complicated objects like foam balls compared to steel ball bearings. That's the intuition. Okay, so I put it in all caps here, max contacts. In my cartoon example here, max contacts is 4. We've got, in this case, 2 cubes that happen to be approaching one another, and they happen to collide face on. This face comes into contact with this face. The physics engine knows roughly that's where the collision is occurring and drops 4 points in there, and I have limited the physics engine to just 4 points. This is something you need to set as the programmer because you know something about how complicated the collisions might be. If you create some objects and you make them very rigid like ball bearings, you might set this value to be very low. If you're creating a soft robot made out of jello and your 2 jello robots are going to bump into one another, or your robots that are made out of soft biological frog cells are going to bump into one another. You've got soft collisions. That's much more complicated. You might set this value to be very high to allow the physics engine a lot of room to maneuver, a lot of ways to simulate this collision. Okay, in my cartoon here, you can see that for each of my contact points, there's 2 arrows pointing out of those points. What do you think those arrows represent? You're all physics engines experts at this point.
The forces pushing.
The forces pushing the objects apart. So what we're going to do, what the physics engine is going to do is create temporary joints. We talked about hinge joints last time. We talked about ball and socket joints last time. There's lots of different kinds of joints in a physics engine, meaning that there are lots of different ways that joints can restrict the positional and rotational degrees of freedom of the objects. Contact points, as you can imagine, they're going to try and restrict the relative motion of the 2 objects that have come into contact. Specifically, it's going to restrict them, or it's going to try and restrict them from moving relative to one another, which would cause them to further interpenetrate. We're going to try and restrict, if these 2 objects come into contact, we're going to try and restrict this relative degree of freedom, this motion between the 2 objects. We're going to do it by basically welding these 2 objects together. That's where you can think of the contact points as like welds, but they're temporary. They're only going to exist for one time step. During that one time step, we're going to weld the joints together. We're going to weld the objects together. We're going to apply forces at those points, pushing those objects apart. And at the end of that time step, we erase all of those contact points again, and the next time step, we do collision detection and resolution all over again. It seems horrendously complicated for this situation in a physics engine. The reason it's complicated, again, is collisions aren't always this and this. You might have 2 partially bundled up balls of aluminum foil, and when they come into contact with one another, assuming they're moving fast enough, they start to deform with one another. Or you work for NASA and you're simulating the skin of the space station, and you're simulating what happens when a micrometeoroid comes into contact with the surface of the space station. Very important that you simulate that collision correctly. Yeah? Okay. Again, a little bit of detail here, a little bit more detail here. For each one of my 4 contact points here, I can set different aspects of how they apply these forces. I can make a particular contact bouncy, meaning when they collide, most of the energy that's going into that collision is going to be applied to the force pushing them apart. If the contact is not bouncy, it's like 2 Nerf balls coming together, then when they collide, there's going to be relatively little force pushing in the opposite direction. It's actually very complicated to simulate. There's a lot of different numbers you can use to simulate how to apply forces when a collision occurs. Any questions about that? This is the most complicated part of physics engine. It's going to get easier from here. Yep?
So for pyrosim or hydraulic in general, does it assume like elastic collisions?
Does it assume elastic collisions? Do they come apart or not? You tell me. You've now been creating objects, and they have collided with the ground plane. You've seen them collide with the ground plane dozens or hundreds of times. You might not have known that you're not necessarily analyzing the nature of the collision. Are they elastic or inelastic collisions? Sorry? There's a little bit of bounce when things hit the ground. So somewhere in between, right? They're not on a trampoline. You don't see them jumping back up to almost the same height that they were before. And they're also not on foam ground. They're not hitting the ground and immediately coming to rest on the ground. It's somewhere in between, which you can change. If you dig into pybullet.py and work your way back, you can set some of these parameters and alter the nature of the collisions in your simulator, but surprise, surprise, we're hiding all of those details from you for now. Other questions? Okay. Okay. Sorry, I said this already. This is just the ODE code that instantiates what I just told you. We create, or the physics engine creates some joints. It doesn't create hinge joints. It creates contact joints, particular type of joints which are, among other things, temporary. They last one time step. Okay. All right, back to PyroSim. What we're going to talk about in a moment when we finish up lecture 6 here is adding in the additional components of robots that aren't in the physics engine itself, including sensors and motors. So in PyroSim, when you simulate a touch sensor and you query what is the current value of the touch sensor for the link called link name, you pass in a string here. This function will return a -1 if that object is not in collision with any other objects, and it'll return a 1 if it is in collision with something else. This function, as you might be able to now see, is exploiting aspects of pybullet underneath. P here stands for pybullet. So in this function here, PyroSim is calling pybullet and asking for all of the contact points that have been sprayed by the physics engine during the current time step. There may be other objects that are in collision with one another at the same moment in time. Here's all the contact points that exist in the physics engine at this moment in time. We now have all of those points collected into a data structure called points here. We're now going to walk through each individual point in this set, and we're going to ask if any of these points are connecting together, or if any of these points involve the desired link that we're interested in. Let's assume this is the one we've just queried, and we're asking, is this object in collision with any others? If the answer is yes, we set the touch sensor to 1. Otherwise, we set the value to -1. Question?
Why are you indexing at 4 in the point?
Aha, okay. So has to do with the data structure itself. So there are 3 numbers that come before in point here for an individual contact point. There are 4 numbers. Actually, there's more than 4 numbers. What do you think some of the other numbers are that describe this individual point? One of them, the 5th index here, because we count up from 0. The 5th one tells us which object it's associated with. What other numbers do you think we need to describe an individual contact point?
Are the first 4 the quaternion of the point?
The good question, the quaternion of the point. A point is one-dimensional, so we don't need to worry about the rotation of the point, but you're very close.
But the orientation of the force that it applies, so you also want to know that.
Great question. Yes, I don't remember whether this data structure contains the forces. I don't know if those have been computed yet. Good question. What goes into a quaternion? There's 4 numbers in a quaternion. One of them has to do with the rotation of the object, which in this case is a zero-dimensional point.
Isn't it 3 orientation numbers and then 1 scaling?
Well, it's 1 orientation number and 3 positional pieces of information. XYZ, where's the object in three-dimensional space? And then the fourth one is how does it rotate along? Oh no, I'm sorry, I misspoke. You're right. 3 of the numbers describe the vector, and the fourth that we align the object along, and then the fourth number is the rotation around it. I was fishing for XYZ. We need the X, Y, and Z position of a contact point. So that's at least 3 numbers. And then this contact point says, I was injected here because the physics engine thinks this object and this object might be in contact with one another. So the 4th and the 5th number are indices, they're describing links. So basically a contact point says, here I am at XYZ, and I'm trying to resolve the collision between link index 1 and link index 2, these 2 objects. Yep.
Is this approach immune to flaws like gimbal lock? Or?
Yeah, gimbal lock, yeah. So gimbal lock has to do with defining rotations. So contact points have nothing to do with rotation, right? Everything is just positional. I'm here, and I'm going to apply linear forces pushing apart. Quaternions help with gimbal lock. Yes. So far, so good? Okay. Someone found a bug between this line and this line. Turns out it's possible for points to return none, in which case you get into trouble here. So if you remember the hotfix I emailed around a few days ago, it was about that. Okay. Okay. Point I want you to take away from this slide is PyroSim is a robot wrapper around the physics engine. Physics engine doesn't know anything about sensors and motors. PyroSim, we're simulating a sensor by exploiting information that the physics engine has already computed for other purposes, in this case, for resolving collisions. Okay. All right. We're almost done with code snippets here. The last and most important piece is putting all of this together. The sim loop. Every physics engine has a sim loop. I can't remember, I think it was assignment 1 where you wrote this for loop, this big for loop right at the beginning. What happens during every pass through that for loop? You're simulating the physics for a very short period of time. When your computer exits your for loop, it updates time by a small amount, goes back into the top of the loop, simulates physics again, again, and again, and again, right? Simulate the physics, simulate the physics, simulate the physics. And when you show all of those frames, you get something, hopefully, that looks like a physical situation. Okay, so what goes into a sim loop? First thing, as we just talked about, is collision detection and resolution. Again, this is a code snippet from ODE written in C. It's different. It's different in your code. The collision space, I think, is hidden from you. But anyways, find out who collided, create all the temporary contact joints, and if the simulation is not paused, step the world. You'll hear this very often when people are talking about physics engines. We're going to update the physics, assuming a certain amount of time elapses from one time step to another. This is the time step length. It's usually in seconds. So in this code snippet here, we're saying that all of the physics that occurs within this world, 0.05 seconds elapse from one frame to the next. Yeah? Okay. During that time, inside this call, in the ODE physics engine, that's where the physics engine would use F equals ma to figure out all the forces that are acting on objects, like gravity and the results of collisions, hinge joints, and so on. Use all of those forces to compute the new acceleration, and from there, the new position, and the new orientation of all the objects. So after D world step, everything has moved and rotated. Throw away all the contact points. Remember, contact points are temporary. They only exist for one time step. And then for every object that's in your scene, draw it. And again, in PyBullet, I think that's all hidden from you. So do collision detection and resolution, step the world, do some housekeeping and cleaning up after the fact, draw everything, rinse and repeat. Okay, put it all together. Questions about that? Okay, before we leave this slide, we're going to have a little discussion about time, because time can be very confusing in physical simulation. There are different time scales at work, and it's important to keep these straight. In the world itself, from the perspective of anything that's in the world, time progresses from by 0.05 seconds. So from one frame to the next, things change according to this. So if this value is large, like 1 second, from one time step to the next, the positions and orientations of objects will change by a lot. If you set the time step to be very small, very close to 0, then the physics engine will only update the positions and orientations by a very small amount. Yeah? Okay. If you have 1,000 objects, n equals 1,000 objects in your scene, it might take your crappy little laptop a very long time to finish with this call. It might take your laptop more than 0.05 seconds to actually compute this. So out here in the real world, every pass through this function, which is one call to world step, might take longer than 0.05 seconds. From the perspective of everything inside the simulation, it's still the same, 0.05 seconds. If you've got n equals 2, you have just 2 spheres that are inside your physical simulation. It might take your computer less than 0.05 seconds to pass through this function once. So far, so good. So we've got wall clock time. How long does it take your laptop to compute the physics for one time step? There's how long things happen inside the world. So we've got 2 different time scales, and they can be different. And the difference between them, which one is running faster and which one is running slower, is a function of how complicated your scene is. Everybody see that? Okay, if things aren't complicated enough, there's a 3rd time scale. You might draw the scene, and you might have the graphics window open, and you may be watching the graphics, or you may be writing the frames of, you might be writing each of these frames to disk and stitching them together in a movie, which you then watch after the simulation ends, or you're watching the graphics window. And your laptop may be rendering those frames and showing you that video at 30 FPS, 30 frames per second. How much time between frames? 0.03, 1/30th of a second, right? 30 frames per second. So the time difference between 2 contiguous frames is 1/30th of a second. There's a 3rd time scale. Very confusing. So you might watch a video, it might fly by very quickly, but from the perspective of everything inside the world, things are still progressing at this time scale. Okay, deep breath. One more time scale. Remember that in this class called Evolutionary Robotics, you've got your robot moving around inside an environment, and there is an evolutionary algorithm that is simulating n robots, throwing away the robots that move slowly and making randomly modified copies of the robots that move a little bit faster. And so we have uppercase T here, which is evolutionary time. Like here in the real world, evolutionary time is very, very slow. Changes over evolutionary time. So there are at least 4 time scales that you're making use of when you finally wrap an evolutionary algorithm around your robot. Okay. Luckily, most of the time it won't matter, but just remember different time scales at play here. Okay. All right. So coming back to now simulating robots inside our physical simulation. As I just mentioned, in PyroSim, if we want to simulate a touch sensor, for example, we can exploit code that's already being used. So in this case here, let's imagine we have a little 2D robot here that has a front leg, a torso, and a back leg. Let's assume the torso is object 1, back leg is object 2, and the front leg is object 3. 1, 2, 3. And at this cartoon moment in time, the back leg is in contact with the ground, which means the touch sensor is firing, represented by the black dot here. At this moment in time, the front leg happens to be off the ground, so the touch sensor is returning a value of -1. It's not in contact with anything. This object is in contact with this object, but we're ignoring that collision because we're assuming the front leg is attached to the torso with a rotational hinge joint. Okay. Let's assume that you want to simulate a light sensor now. Remember at the beginning of the course, I was showing you the robot that grasped that blue object and lifted it onto its back. From the perspective of the robot, it was actually an object that was emitting blue light. That's how it was able to find it. How would you simulate a light sensor by exploiting aspects of the physical simulation that's running? Now that you know some aspects of the physics engine, what might you exploit? Contact points, probably not going to be very useful here.
Would you cast like vectors from the light source and see which hit the object?
We could do some ray tracing, so we could cast or emit vectors that leave the light source, and we could see whether they hit the robot. We could do that. It might be computationally inefficient because we would probably send out vectors in every direction, and only a very small number of them would hit the robot. So it's a good starting point. It's a good conceptual sketch about how to simulate a light sensor. We're going to have a whole bunch of vectors emanating outward from this light source here. Sorry, I should have said this. We'll assume object 4 is the light source. But it's wasteful. Can we do a little better?
You can draw a line between the light sensor and the object and see if the line is blocked, and the distance the line takes up.
Absolutely, right? So we can draw a line from object 4 to object 1, and a line from object 4 to object 3, and a line from object 4 to object 2, and see whether that line is quote-unquote hit by something. How do we know how to draw this line? We ask the physics engine. Remember, the physics engine knows the x, y, and z coordinate of every object at every time step. It's already computed that for us for collision detection for other things. It has that information on hand. So if we could ask for the x, y, z of object 4. And let's just do object 1 here. And we could connect them by a line. And sure enough, we could see that this line, if we connect it, this line would enter the inside of object 1. We could actually go back and exploit collision detection by telling the physics engine there's a very thin, long rod here. You can actually do that. And if it says object 1 is in collision with this very long rod, that's the light hitting the object. We could do that. It's a little complicated. Simplest thing is just take the two positions of object 1 and object 4 and take the distance between them, take the Euclidean distance between object 1 and object 4, and then compute the light level, the amount of light arriving at object 1. We're going to compute it as 1 over the distance squared. Why?
The inverse power law.
The inverse power law, or the inverse square law. So if you think about light emanating in all directions from the sun, all that light intensity, the further away you get from the sun, the amount of light you actually feel falls off quadratically. If you move twice as far away from the sun, you receive a quarter of the amount of light from the sun. So we've taken some information out of the physics engine, positions of the objects. We've incorporated some additional physics into the physics engine, the inverse square law, which gives us a pretty good approximation for the amount of light that's arriving at the center of object 1. This assumes that object 1 is made out of transparent glass and all the light gets all the way into the inside. If it's opaque, we're really asking about the amount of light that falls here, and getting this position is a little more complicated. So we could keep adding more and more complicated code to make a more and more accurate light sensor. You've probably already figured this out, but the physics going on inside your physical simulation isn't a perfect match to the physics that's occurring out here. It's all an approximation, and it's up to you how much or how little you want to approximate actual physics. So far, so good? Okay, details don't matter except that we're just exploiting stuff the physics engine is already doing. Okay, that's sensors. How are we going to exploit the physics engine to create a motor? Let's continue on with our little cartoon 2D robot here, front leg, torso, back leg. And at this moment in time, we're assuming that the front leg is off the ground and the back leg is off the ground. We're going to assume that we want to simulate a motor that is sitting at the front shoulder joint, right up here. The rotational joint that connects the front leg to the torso. We're going to assume at this moment in time that we want the front leg to rotate outward to 60 degrees in front of the robot. In this class, we're going to talk about extension, which is body parts that are moving away from the main part of the body, and flexion, rotations that are bringing the objects towards the center of the body. For the purposes of this class, it's kind of arbitrary, but we're going to pick positive numbers to represent extend away and negative numbers for flex toward. Okay? Positive numbers extend, negative numbers flex inward. Okay, so this is a number that we've come up with outside. Soon it will be the neural network controller that will dictate this, but for our simple cartoon example here, this is the current state of the robot, and we want the motor to rotate the front leg out. We want it to extend the front leg out to 60 degrees in front of the robot. It's currently at 0 degrees. When you set up your simulation and you connect two objects together with a rotational joint, the current angle of that joint is 0 degrees. This can be very confusing. If you connect two objects like this, the angle at the joint is 0 degrees. If you connect two objects together like this, at time step 0, the angle of the joint is 0 degrees. 0 degrees, 0 degrees, 0 degrees. It doesn't matter from the physics engine's point of view. Hopefully for most of you intuitively, this feels like 90 degrees, right? It's a little confusing. Everything is going to start at 0 degrees. So what this cartoon is telling us at this point in time is the current angle of the joint is 0, and we want that joint to extend the front leg away to 60 degrees, rotate it outward to 60 degrees. So far, so good? Have I lost anyone? Okay. All right, let's jump back to some, again, this is ODE code here. So we are setting, in this case, we're going to set a parameter of the hinge joint. We're setting that parameter to be the motor force. This is the maximum force the joint can handle. If you were to build this robot in real life, you could take a little teeny tiny hobby rotational motor and attach it to the shoulder joint. If your robot weighs 200 pounds, you probably didn't choose the right hobby motor. You could take a big jet engine motor and add it to this robot. If your robot weighs a couple of pounds, it's probably overkill, right? So what this line here is doing is telling the physics engine how strong the motor can be. What is the maximum force that this motor can ever apply? Okay. All right. We then also tell the physics engine at this moment in time, we want the desired angle of the front leg to be 60 degrees. That's the desired angle. And we now call, this is the physics engine itself, we query the physics engine, what is the current angle of the joint? As I just told you in this cartoon time step here at the beginning, the actual angle is 0. So we've got a desired angle of 60, an actual angle of 0. 60 minus 0 is 60. The difference between the desired and actual angle is 60. We then send this information back into the physics engine. in this case ODE, we send it the difference, and we tell it to, we send that difference in, and we tell the hinge joint to use that to set the velocity of the objects connected by the joint. It's a little confusing, so I've tried to paraphrase it here. What this line is doing is telling the physics engine, hey, physics engine, apply force proportional to how far the joint is from where it should be. If difference is big, the hinge joint is going to apply a lot of rotational force to the two objects that that joint connects. If diff is 0, the hinge joint is going to behave like a rag doll. It's not going to apply any forces to the two objects that it connects. So far, so good? So we're going from a desired angle to ultimately the physics engine computing a force that it adds to the objects. Remember, the ultimate or the deepest currency in every physics engine is forces. The physics engine, every time step, is summing up all the forces that are acting on an object and then determining how to change the position and orientation of that object accordingly. Okay, so I've told you that positive numbers, and this difference is positive, 60 minus 0 is 60, so we're sending 60 in here. So at the next time step, the physics engine is going to apply a force that's going to try and rotate this object away from this object. But it's a force. It's going to apply a force. So the front leg is going to start to rotate forward. It's going to start to extend away from the torso. The front leg is not going to immediately assume 60 degrees away from the torso at the next time step. We're dealing with forces and accelerations now, which were derived from a desired angle. So far, so good? Okay, so let's imagine this is the situation at the next time step. Whatever this force was that was calculated and applied by the physics engine, it's caused the position and orientation of this object to change such that now this object is rotated or extended 20 degrees away from the torso. We still want the desired angle to be 60. We're keeping the desired angle the same. Now the difference is 40. We have a desired angle of 60. We have an actual angle of 20. 60 minus 20 is 40. So now we're sending 40 into this function. What does the physics engine do with that information? How does it handle this new information, 40 rather than 60, differently?
It reduces kind of the torque that's applied, so it slows down as it gets closer.
It reduces the torque. My apologies, I don't know that I've mentioned this before, again, for the people who don't quite remember their high school physics. When we talk about force, if I use the word force, it's usually linear force, something that is pushing on something. Torque is force that tries to rotate something, rotational force. Yeah? So the rotational force that the physics engine has computed is less because the difference is less. So in my example here, this is a cartoon. The front leg should have rotated actually a little bit less because there was a little bit less force applied. Everybody see that? The initial angle of the joint was 0, then it was 20, now it's probably 38, and gets smaller and smaller. It's changing. The angle is approaching 60 degrees, but as it approaches, it's slowing down. So if we were to now, I want you to run this simulation in your head, and you should see a mental movie of the leg rotating forward quickly, slowing down, slowing down, slowing down. Does it stop when it reaches 60? In this cartoon example. I see somebody shaking their head no. Why not?
Because it's kind of just approaching it as like an optimum, and then once it gets there, it's just going to kind of jitter back and forth and apply forces to counteract the motion away from that point.
Yep. For the engineers here, this is going to be blindingly obvious, but for those that haven't seen control theory before, which is what we're now talking about, we're trying to control this rotational joint, it's actually more difficult than it might look. So this front leg might approach, and it might actually get to 0. It might get to 60, in which case the difference is 0, which means the physics engine says, my job is done. I'm not going to add any additional forces to this object. But in this universe and in the physics engine, there's this thing called inertia. And so the acceleration or the movement of the front leg, because the front leg has mass, might carry it beyond 60 degrees, maybe to 63. Now, desired angle is 60, actual angle is 63. So at the next time step, 60 minus 63 is minus 3. What does the physics engine do now? It starts pushing or applying rotational force in the other direction. So now it's at 63. It comes back to 58. Physics engine applies force. So what you might get is what you wanted was to simulate a front leg swinging forward and coming to rest at 60. You might get a leg that starts to do this, which you don't like. So maybe you put a little number in front of diff, 0.5 times diff. You try and decrease the amount of force that the physics engine is applying. And so now, if you put a 0.5 times diff, at every time step, the physics engine is only going to be applying half as much force to rotate the front leg. So now it starts to rotate up towards 60 degrees and stops. Gravity's pulling it in the other direction. It doesn't quite reach 60. So you change this 0.5 to 0.9. Now it goes back up and starts oscillating around the set point. You go back and set 0.8 times. You get very frustrated very quickly. There are whole branches of engineering, control engineering, dedicated to trying to handle this problem. We're not going to try and solve this problem in this course. I saw somebody had a question. No? Okay. Okay. All right, we are not going to solve this problem because in reality, you're not going to be going into the code and setting a desired angle to be 60 degrees. Your neural network controller is going to do it. So already this morning we've talked about links or objects, joints that connect them together, sensors, motors. Let's talk about neurons now and synapses. So let's imagine we have a very simple neural network controller inside our robot now. We've got one sensor neuron, a second sensor neuron, and one motor neuron. I've changed my cartoon example a little bit. We're assuming at this moment in time, the touch sensor in the back leg and the touch sensor in the front leg are both firing. So we take those two touch sensor values, 1 and 1, we plug them into the two sensor neurons. And I haven't told you what these synaptic weights are yet or what the activation threshold is down here. We're going to just assume that the value that arrives down here is 60. The number that sits inside of a motor neuron, as the name of the neuron implies, is a command to a motor. So this motor neuron is going to send 60 to the joint. And in essence, the brain of the robot, or more specifically, this motor neuron is telling this joint, apply some force to get this leg out to 60 degrees. We just saw how this works through the code snippet. So 60 degree, the desired angle of the joint is 60. That goes into the physics engine. The physics engine applies a force to the front leg. The front leg starts to extend outward. And the moment it does, at the next time step, no matter how much it rotates forward, by rotating forward, it pulls the front leg off the ground, which means that the touch sensor inside the front leg stops firing. That's what the white circle represents. Which means now, at the second time step, we're feeding in 1 and 0 to the sensor layer. We've changed, the numbers arriving at the sensor layer are different. When we propagate those values through to the motor neuron, like we talked about in the neural network lecture, in my cartoon example here, imagine that the value arriving at the motor neuron is minus 90. Doesn't matter how I got that number, let's just assume it is. What happens at the next time step? The motor neuron is telling this joint to rotate to minus 90 degrees.
It's gonna start going back the other direction.
It's going to start going in the other direction, right? It's a negative number. Negative numbers always represent a flexion, rotate inward towards, and the magnitude of this number is greater than the magnitude of this number. So it's actually saying flex inward with greater force. The physics engine is going to try and apply torque to rotate the leg in the other direction, and the leg's going to start coming back down again towards the ground. What happens at the next time step? And the next time step, and the next one. Animate this hypothetical physics engine in your head. What starts happening?
The second it touches the ground again, it's going to go back to the 20 degrees and then just bounce back between these 2 points.
It's going to bounce back and forth. You're going to have a robot that kicks its leg up in the ground and then immediately rotates it back, kicks and oscillates. And possibly every time the front leg hits the ground, it's going to pull the robot forward, assuming the back leg isn't doing anything. Suddenly we have locomotion. Where is the oscillatory signal inside the system? Where's the clock that's measuring the frequency of this oscillation? Where's the component in the brain of this robot that says, oscillate the movement of the front leg?
T2.
Partly. So this is kind of an unfair question. The answer really is it's nowhere. There is no explicit oscillation. You notice that we're not calculating sine of or cosine of anywhere, which usually you do when you're trying to create an oscillatory pattern. That oscillatory pattern emerges from the interaction between the brain of the robot and the body of the robot. This is the heart of embodied cognition. When we talked about embodied cognition before, we talked about René Descartes and the nature of the soul in the 1600s. That's the philosophical side of embodied cognition. Here's the nuts and bolts engineering side of the same thing. This robot does not think up, I would like to oscillate my front leg, so I will do the following. There is none of that. There's just this pattern, this oscillatory pattern emerges from the interaction between the brain of the robot, its body, and its surrounding environment. Okay, we're going to see lots and lots of more examples of that. Most of all of robotics is predicated on this idea that if we want robots to act autonomously and safely in this world, we're not going to be programming into the robot, do this and make sure that you don't hurt any humans along the way in the following way. Do this, don't do that, and also don't do that, and also don't do that. We are going to try never to tell the machine to do something explicitly. We're going to hope that the thing that we want arises implicitly out of the careful design of its physical body and its neural controller. This is kind of like a Bratenberg vehicle, very, very simple, but illustrates this idea. Okay, just to remind ourselves about artificial neural networks, I haven't told you about the synaptic weights here, and I haven't told you about the activation function. Let's keep things simple. Let's assume there is no activation function. Assume that minus 90 is a raw weighted sum, and assume that 60 is a raw weighted sum. No activation function whatsoever. What are these two synaptic weights? Remember that we calculate the value of this neuron by taking the value of this neuron times this weight plus the value of this neuron times this weight. Don't worry, it's not this hard. It's not too hard. Yep.
T1 has a weight of negative 90 and T2 has 170.
Okay, great. So 1 times something plus 0 times something has to be minus 90. So the only answer here is this has to be minus 90. 1 times minus 90 plus 0 times something is minus 90. So we got one of these two synaptic weights figured out, 90. Now we need 1 plus 90 times 1 plus something else to come out to 60, which is, what did you say?
170.
170, is that right?
Yeah.
Plus 170. Minus 90, 170. 1 times 90 plus 1 times Did I get that right? Sorry, 1 times minus 90 plus 1 times 170 is 60. If you didn't work that out for yourself, it's okay, but just a reminder, this times this plus this times this gives us this number. So far, so good?
It's 150.
150, thank you. Didn't have enough caffeine this morning, not 170. Minus 90 and 150. Okay, thank you. All right. What would happen if we change these two numbers? We go back to this starting state, and we leave everything the same except we change these two numbers. What happens? The robot moves differently. I don't know how it moves differently, but it moves differently. What is your evolutionary algorithm going to do? It's mostly going to start to fiddle with synaptic weights to try and get the robot to move more and more in the way that you want it to move. 150. Okay, there we go. All right. Any questions about lecture 6? Took a little longer than I was hoping. That's all right. We'll switch to lecture 7 in a moment. Question?
When you're picking your the torque on your motors, are you generally trying to choose like motors that you have available? Like you mentioned the hobby shop motor.
Okay.
Try to go with something.
Good question.
Reward for it.
The question you're asking about is sim to real. So assuming we're simulating a robot and we ultimately want to create a real robot, how do we go about simulating the motors? The answer is yes. So we know that the real robot is going to weigh about 170 pounds. The front leg is going to weigh about 30 pounds. We might work backwards to what's the maximum amount of torque that's going to be needed. If you've got a 140-pound body and a 30-pound front leg attached, a hobby motor probably ain't going to cut it. You're going to go looking for a different motor, right? So yes, we're trying to make decisions here that inform how we go about doing this. We're going to spend a lot of time talking about exactly this in a few weeks' time. Yep.
Like building off that, are you able to have it evolve that max torque value and then like constrain it so maybe you can't go above this, but figuring out what motor is optimal for it?
Excellent. So now you're starting to think like an evolutionary roboticist. We could try and manually work backwards and do some good engineering to figure it out. It's tricky. It's not as easy as it looks. So why don't we just take the lazy route and let the evolutionary algorithm figure it out? How might we do that? You remember, hopefully from lecture 5, a pre-recorded lecture from last year. Last year I mentioned the evolutionary algorithm has a fitness function, right? This is the equation that says try and maximize the following. It might be maximize horizontal displacement. Move as far to the right as you want, as you can. So imagine our fitness function f, we're just going to set it equal to x, how far the robot moves in the positive x direction. We could multiply it by tau, the total amount of torque that the physics engine uses to get the robot to move to the right. What would happen if we ran an evolutionary algorithm that was trying to maximize f? What would we get? We'd get a robot, hopefully, that moves in the positive x direction.
You get a robot with a lot of torque.
Actually,
Need it or not.
we'd get the opposite of what we wanted, right? We'd get something that's really, literally throwing its weight around, not what you want a safe robot that weighs 170 pounds to be doing. So this was a bad choice. Can we do better?
Subtract tau.
Okay, better, right? Maximize horizontal displacement and minimize torque. Yeah? Okay, we're going to see a lot of different fitness functions in this class and a lot of different roboticists trying to get this equation right. Okay, great question. Any other questions? Okay. So on to lecture 7, the very first years of evolutionary robotics. In lecture 7, we're going to look at 2 experiments that were conducted at more or less the same time in the early 90s. So these are basically, there were sort of 2 independent discoveries that you could get an evolutionary algorithm to design robot behavior automatically for us. You can tell from the grainy picture here that we're now in the very early 1990s. We're going to talk about the Italian approach and the English approach. We'll start with the Italian approach. They used a brand new robot at the time called the Kepra robot. It was built around 1996. It was developed at EPFL in Switzerland, so Italian researchers in Switzerland. It's confusing. We'll call it the Italian approach. This robot is basically like a hockey puck, so it's 55 millimeters across, metric system. It was small, which meant they could do experiments on a table rather than in a large arena. The other nice thing about the Kepra robot is it had a modular architecture. So it's got this cylindrical body. You can see it's got these two little wheels on either side, and you could stack modules on top. You could add a little camera on top. You could add a little gripper, like you see in the upper right here, and the gripper is grabbing a little sugar cube. Little cylindrical robot with a left wheel and a right wheel. Sound familiar? Where have we seen this before?
Roomba.
The Roomba, maybe you have it at home, right? Every good idea was preceded by the same good idea. Yes, the Roomba was inspired by the Kepra robot and the Bratenberg vehicles, right? All kind of the same thing. Simple machines with a left wheel, right wheel. Okay. I haven't followed this link for a couple of years now. I think you can still buy your own Kepra and play around with it if you like. Okay. Right. All good ideas have earlier good ideas. If you got anything from Amazon recently, it was probably in a warehouse somewhere sitting on a shelf, and that shelf was picked up by an orange robot that looks exactly like this, and that tower of things was brought maybe to a human worker, maybe to a robot, and they plucked out your AirPods and dropped it into the envelope for you. This robot also inspired by the Kepra robot. Okay, doesn't seem very obvious, but you were surrounded in this world by robots that have more or less the Kepra architecture. Okay. In the very first experiment we're going to look at today, they put a little, it's not quite a camera, they put a visual sensor on the top. This is a linear vision module. It's much more actually like an insect eye than our eye. You can think of this linear vision module sitting on the front as having 64 beams of light, and the robot can detect how long those beams of light are before they're broken. It's kind of scanning the world in front of itself. And it covers a front visual field of about 36 degrees, so about this. This little picture here is meant to represent kind of what the robot is seeing. It might be, the robot might be looking at a cylindrical barrier, so the beams directly in front of it are being broken or only half as long as the other beams. Or it might be looking at a wall that's got a black band in the center. This early visual camera couldn't distinguish between obstacles and patches of darkness compared to lightness. Doesn't really matter for our purposes, but just trying to take you back to the mid-90s, early mid-90s here. Okay. What these researchers wanted to do was to create a little neural network for the Kepra robot, drop that neural network inside the robot, let the robot move around on top of a table for about 10-15 seconds, compute fitness, how well the robot does at whatever they wanted it to do on the top of the table, take out the neural network, drop a different neural network with different synaptic weights into the robot, which means the robot's going to do something different on top of the table, measure F for that little neural network, again and again and again, and at the end they would have fitness values for 100 different neural networks. Delete the 50 neural networks that have lower F values and make randomly modified copies of the surviving neural networks. That was the idea they came up with, which became the field of evolutionary robotics. Okay, sounded great, sounded easy, not so easy with 90s technology. So how did they pull this off? Well, first of all, there was no Wi-Fi or Bluetooth, very difficult to do wireless stuff. So they took their little Kepra, they attached it by a cable to the computer. Kepra is very small, dragging a cable behind it wasn't possible, so they had to hang it from a ring. There was some little sort of MacGyver engineering they had to do to get this to work. They couldn't run the neural network on site, couldn't run the neural network on the robot, so they ran the neural network on this desktop. So the evolutionary algorithm and the neural network itself were running in, the brain of the robot was running inside the desktop. They would take the values arriving at the motor neurons. There's 2 wheels, so there's 2 rotational motors. They had 2 motor neurons. They take the values from the 2 motor neurons, send them along this cable to the robot. The robot would move a little bit, and then there was a laser emitting device sitting in the upper left corner here that was emitting a laser into the workspace or bathing the top of the desk with these lasers. And again, the lasers were connected to the desktop. They could work out from the response of this laser emitting device, they could figure out the horizontal position of the robot on the table and alpha, the heading. Where was it? Was it facing north, northeast, northwest on the top of the table? So at every point in time, or for a few points in time, they could get X, Y, and alpha, the position and orientation of the Kepra. They could then take that X, Y, and alpha information, those triplets of numbers that would span 10, 15 seconds, maybe they'd have 180 or 220 numbers, and they could use it to compute F. They could get it to the robot to do something. If you put a robot on this table here at the front and it was driving around for 10 to 15 seconds, what might you want to evolve it to do? Not much it can do. It's a pretty simple environment. Stay on the table, probably a good thing to do. You start your evolutionary algorithm, figures out how to do that. It evolves synaptic weights of 0, which causes the robot to do what? Nothing. The robot stays still and says, I evolved to do exactly what you wanted me to do. Maybe a mild form of perverse instantiation, right? Okay, great, you could do it. They probably did that and then said, let's try and get it to do something maybe a little bit more interesting than that. So they got some foam blocks out and they built a little racetrack for their robot down here. Again, I apologize for the quality of this image. So they're going to evolve a neural network that looks like this. We'll talk about it in a moment. They're going to evolve the neural network so that the robot circles through the maze as quickly as possible and doesn't bump into the walls. Okay, that's F. All right, so we've got our 2 wheels over here. Here's motor neuron 1, motor neuron 2. They're drawing their neural network right inside the robot to just help you understand the relationship between the sensors of the robot, the motors of the robot, and its neural controller. Remember that in reality, the neural network is running off on the desktop. We've got our 2 motor neurons here. We have 1, 2, 3, 4, 5, 6 proximity sensors. I'm sorry, I misspoke. So here's the linear vision module here. They did not use the linear vision module for this experiment. They used proximity sensors. These are sensors that send out one beam of infrared light. And if that beam of infrared light hits something and bounces back, and the sensor recovers some of that infrared light, the time of the emission of the pulse of light and retrieving some of that light back tells it how far that pulse of infrared light traveled. So for our purposes, you can just think about these 6 sensors on the front as returning a floating point value, a number that represents how far away an obstacle is from the robot. So this sensor would report a value of 0 or near 0 if there's no obstacles or a distant obstacle. An obstacle that gets closer and closer and closer, the more strongly the proximity sensor fires. The greater the magnitude of the value at that sensor neuron. There was also a 7th and 8th proximity sensor on the back of the robot. So we've got 8 sensors, and you'll notice that there are arrows going from the 8 sensor neurons in towards the motor neuron. Usually when we draw a neural network, we put the input layer up here and the output layer down here. Here's the output layer here, and here's the input layer on the periphery. So far, so good? Okay, again, I haven't had my caffeine this morning, but you can count up all the arrows in this picture. That's all the synapses. They're going to evolve weights for those synapses so that when you put those synaptic weights into the physical Keppera, it's going to circle around the maze as quickly as possible and not hit the walls. We just talked about sim to real. We spent some time talking about physics engines. No physics engines here. This is the mid-90s. Commercially available physics engines didn't exist yet. They started to arrive around 2000. So no sim at all. This is just real. They're going to evaluate every neural network for about 10 or 15 seconds on the physical robot. You'll notice if you squint carefully, hopefully you can see this, some of the arrows have this kind of head, and some of the arrows have this kind of head. They're meant to represent excitatory and inhibitory connections. The researchers manually set some of these synapses to be excitatory, and they set some of them to be inhibitory because they wanted to reduce the amount of effort on the evolutionary algorithm. They're working with a 90s desktop and a 90s robot, so they're building in some assumptions. What can you tell me about where the excitatory synapses are and where the inhibitory sensors are?
The inhibitory ones are towards the middle, from what I can see.
Okay.
So it if those if it's not seeing anything there, then it gets reversed and it goes it'll try and say towards the middle. So right.
Okay.
Is that right?
Close. Other observations?
It looks like the three in the front on the opposite side of the motor are inhibitory, so it's kind of mimicking the powered brake converter vehicle, and then the two back ones are excitatory to kind of push it forward away from it. If it's in back.
That's it. Let me start with your last observation. So the ones at the back are all excitatory. More proximity at the back, the more the wheel should rotate forward, right? Move away from anything that's behind you. So they're giving the robot a strong hint. They're setting the sign of the synapses, but not the magnitude. The magnitudes are going to be worked out by the evolutionary algorithm. As you pointed out, if you look at, for example, the three front left proximity sensors, the contralateral connections, the ones that cross the side of the robot, those arrive as inhibitory connections. So contralateral inhibitory connections do what? If we have more proximity over here, they more inhibit this wheel. More proximity to the front left slows the right wheel, which causes the robot to do what?
Turn away from an oncoming.
Turn away. So they're kind of building in collision avoidance already. They're giving it the basic idea. Exactly how quickly and how much it turns away is going to be dictated by the magnitudes of these synaptic weights. What are the ipsilateral, same side excitatory connections? What are they doing?
They're then exciting that one motor to speed up even more and turn faster.
They're adding to collision avoidance, right? So if there's more proximity front left, turn the left wheel more. Okay. So there's the neural network architecture over here. A couple more details for you. The wheels can spin forward and spin backwards. So we've been talking about rotational joints and extension away and flexion towards. Now we're talking about rotational velocity. So negative rotational velocities mean spin the wheel back. Zero rotational velocity, hold the wheel still. Positive values represent forward rotation. So the values arriving at the motor neurons can be positive or negative values, and they can dictate how the motors turn. We've got 1 minute left, so I'm trying to get to some of the action of the actual robot. The proximity sensors return only positive values. 0 if the object is very far away, 0.9, 0.8, 0.7, 5, 4, 0.3, 0.2, 0.1, 0. Okay. I want you to take this information. Assume that you have these 10 numbers. You have the values of the proximity sensors. You've dropped a neural network inside the robot. The robot has moved around for 10 to 15 seconds, and you have the average value of these 1, 2, 3, 4, 5, 6, 7, 8 sensor values. Let's assume that I1 through I8 are average values, average proximity values, and VL and VR are the average rotational velocity of the left wheel, and VR is the average rotational speed of the right wheel. For homework, I want you to try and take all of these 10 variables, put them into a function that if an evolutionary algorithm tried to maximize phi, tried to maximize this fitness function, you'd get a robot that circles through the maze as fast as possible and does not hit the walls. Okay, you have a quiz due tonight at 11:59 p.m. You're working on 3 or 7 and 8. See you on Thursday. Thank you.